A nail, that's all it takes. A self-driving vehicle packed with AI, radar, cameras, and millions of lines of software can still be stopped by a piece of metal worth less than a penny. That contradiction is forcing engineers to ask an uncomfortable question. Why does one of humanity's most advanced machines still depend on one of its oldest technologies? The answer is leading to something unexpected. Because the future of the wheel may not have air, it may think, it may adapt, it may even stop looking like a wheel, and what's happening right now inside research labs and engineering teams could fundamentally change transportation over the next few decades. The strange thing is that the wheel is already one of the most successful technologies ever created. For over 5,000 years, its core idea barely changed. Empires rose and fell, steam engines arrived, computers arrived, the internet arrived, the wheel stayed. In engineering, that level of longevity is almost unheard of, which is why many people assumed the wheel was a solved problem. Then vehicles became software-defined, and suddenly engineers noticed something odd. Modern vehicles can navigate city streets autonomously. They can process enormous amounts of data in real time. Yet the only component touching the road remains surprisingly fragile. Air. A modern tire depends on maintaining exactly the right pressure inside a flexible rubber structure. Lose that pressure, and a vehicle worth tens or hundreds of thousands of dollars can become stranded. So engineers asked a radical question. What if the air disappeared? Companies such as Michelin and Bridgestone have spent years developing non-pneumatic tire systems designed to eliminate punctures entirely. At first, the solution sounds obvious. No flats, no blowouts, less maintenance. Problem solved, except engineers discovered something unexpected. Air wasn't just the weakness. Air was also part of the solution. It absorbs impacts, dampens vibration, distributes forces. Remove it and new problems emerge. Heat, noise, ride quality, durability. Suddenly the challenge wasn't replacing a tire, it was replacing physics. And that's where the story gets interesting. Some researchers are now developing advanced structures inspired by metamaterials, engineered geometries whose behavior comes from shape as much as material composition. Instead of a wheel having one fixed set of properties, future wheels could potentially adapt stiffness and load characteristics depending on terrain and operating conditions. In other words, the wheel itself may become dynamic. But even that may not be the biggest change, because engineers are starting to treat the wheel less like a mechanical component and more like a sensor platform. Think about how a human drives. You see the road, you hear the tires, you feel grip through the steering wheel. Autonomous systems don't have those instincts. They need data, lots of it. Researchers are developing smart tire systems capable of measuring temperature, deformation, traction, wear, and road conditions in real time. That means the wheel may become the vehicle's earliest warning system, not reacting to a skid. Predicting one? Imagine a vehicle detecting black ice before the occupants realize the road surface has changed. The wheel would no longer just carry the vehicle, it would inform it. And once a wheel becomes a sensor, another question appears. What if every wheel had a digital twin? A virtual model continuously tracking stress, temperature cycles, fatigue, and remaining lifespan. Instead of replacing tires after a fixed interval, vehicles could predict failures before they occur. Maintenance shifts from scheduled to predictive. The wheel becomes software-defined. But another engineering team looked at the problem from a completely different angle. They asked, why are we sending power to the wheel at all? For over a century, vehicles relied on transmissions, drive shafts, differentials, and axles. Entire systems exist for one purpose: delivering power from a motor to a wheel. In-wheel motor technology challenges that assumption. Move the motor into the wheel itself, and large sections of the vehicle architecture can disappear. Fewer mechanical systems, independent wheel control, new vehicle layouts, more interior space. Suddenly, the wheel isn't just supporting the machine, it's helping define the machine. And then the definition of a wheel starts breaking down entirely. Look at modern robotics. Many autonomous robots no longer use conventional wheels. Some use omnidirectional wheel systems that move sideways, diagonally, or rotate in place. Others combine wheels with leg-like mobility. Engineers developing planetary rovers have experimented with shape-recovering metal structures capable of surviving terrain that would destroy traditional tires. The future isn't converging toward one perfect wheel. It's diverging into dozens of specialized forms, which reveals something surprising. For most of history, wheel innovation focused on materials. Better wood, better iron, better rubber. Now the focus is shifting toward intelligence, sensors, machine learning, predictive models, adaptive structures, software. The wheel is evolving from a passive component into an active system. And that may be the biggest transformation of all, because when people imagine the future, they usually focus on artificial intelligence, robotics, or autonomous vehicles. What they rarely notice is the technology underneath all of them. The 4 points where machine meets reality. For 5,000 years, humans adapted themselves to the limitations of the wheel. The next generation of wheels may do something unprecedented. They may adapt themselves to us. And when that happens, one of humanity's oldest inventions could become one of its most advanced.